All right, so we're going to continue with the integration by parts formula here. We introduced this previously, and of course the idea is we have to choose the u in that so that the derivative gets simpler. And of course the dv then has to be something we can integrate. Now the choice of u in order of preference would be given by the acronym LIATE as a nice way to remember it. So log would be our first choice, then inverse trig, algebraic trig, and exponential would be our least likely choices. So I want to go back and look at the integral of the natural log of x. And that was the one we were looking at. And I said, what is the antiderivative of the natural log of x? Is it 1 over x? No. The derivative of natural log of x is 1 divided by x, not the integral. Okay. But you say, how can I do this as an integration by parts? There's no product, it's just natural log of x. Well, what I'm going to do is I'm going to choose u to be the natural log of x, which is a good idea, right? Logarithmic is our first choice for u, so that's good. Then what's the dv going to be? Well, it's just the dx. I'm going to choose u to be the natural log of x, and therefore my du is 1 over x dx. My dv is dx. Integrating both sides of this, I get v is equal to x. All right? And so now I can evaluate the natural log function, right, by the integration by parts formula. And here it is, right? The integral is of u dv is what? U times v. So u is natural log of x, v is x, minus the integral of v du. v is x, du is 1 over x dx. But when I simplify this first, before evaluating, what is x times 1 over x? That's just 1. And I'm left with the integral of 1 dx. What's the integral of 1 dx? What's the antiderivative of 1? Answer x. And so my answer for the antiderivative of natural log of x is x times the natural log of x minus x. And I want you to check and verify that. Take the derivative of this function here and show that you indeed get natural log of x. Take the derivative of this function here that we've circled and show indeed that its derivative is natural log of x. Okay, that is the antiderivative. Okay, so we can find antiderivatives of functions like the natural log of x, and we can also find the antiderivatives of functions like the inverse trig functions. I'm going to look at the next one involving the inverse tangent function. Also notice this one is a definite integral. A definite integral. So what I'm first going to do with this definite integral is, in order to evaluate the definite integral by the fundamental theorem of calculus part 1, we need the antiderivative, right? So I want to look at just the indefinite integral. What's the antiderivative of the tangent inverse function? So I first want to look at that. So what I'm going to choose is, what I'm going to choose for u? Well, log is my first choice. Then what's my second choice? LIATE, L-I. I is inverse trig. Inverse trig. I'm going to use u to be the inverse tangent function. That means dv is dx. So remember, I differentiate here. So du is what? Well, what's the derivative of the inverse tangent function? Do you remember? It's 1 divided by x squared plus 1. So this would be dx over x squared plus 1 is du. Here we get what? V is equal to x. We integrate. Remember, we integrate dv, we differentiate u. And so this thou is the integral of u dv, and it's going to be u, which is what? Tangent inverse x, v, which is x, minus the integral of what? V du. And what was v again? V was x. And what's du? Well, du is all this stuff. Okay. Did our integral get simpler to do? Again, we don't know what the antiderivative of tangent inverse x is. We know what the derivative is. We don't know what the antiderivative, that's what we're trying to find here. And so I've got x times tangent inverse x, and let's clean this up a little bit. This will just be the integral of x dx over x squared plus 1. So is this simpler to do? Can we do this one? I submit to you we can. I submit to you we can. And let me show you how we're going to do this one. It's by substitution. Okay, you say what's the, so I'm going to use substitution. And I'm going to use the letter u, but keep in mind the letter u I use for this integral is not the same as the u over here. Okay, so just have to realize that if you want to use a different letter for the substitution like w or something, that's fine. We'll use w. How about that? I'm going to let my w be x squared plus 1. So I'm going to get 1 over w, hopefully, which if you remember 1 over w dw, that's a log form, right? We evaluate it as a logarithm. Let's see if it works. dw is what? What's the derivative of x squared plus 1? That's 2x. So dw is 2x dx. And I've got an x dx, and so I just need a factor of 1/2, which gives me my x dx. And so this then becomes, this 1/2 comes out, the integral of what? 1/2 dw is x dx. I've got the dw on top over what? X squared plus 1 is just w. So what's the integral of 1 over w? It's the natural log of the absolute value of w plus a constant. Well, what's w? It's x squared plus 1. So this is 1/2 natural log, and I'm just going to do in parentheses x squared plus 1. What happened to my absolute value bars? You could do it, but you don't really need it, because why? X squared plus 1 is always positive for any value of x. And that's the way I'm going to write it out. And so my answer is that the antiderivative of tangent inverse x is x tangent inverse x minus 1/2 the natural log of x squared plus 1 plus c. Okay, so that's the first step. Remember, we were looking at the definite integral. So now let's go back to that problem. We're looking at the definite integral from 0 to 1. So let's now use what we have. Hence, we can now do what? We evaluate this antiderivative minus the plus c at 1 and at 0. So this will be this whole thing evaluated at 1 and at 0. So we've got some work to do in just evaluating. Replacing x with 1, I get 1 times tangent inverse 1, so that's tangent inverse of 1 minus 1/2 natural log of what? 1 squared plus 1? 1 plus 1? Natural log of 2. Okay, so there's the evaluation at 1. And now at 0, of course, 0 times anything is 0. But don't forget here, I'm going to have what? Minus 1/2 0 plus 1 is 1. But what do we know about the natural log of 1? That is 0. So this whole part is 0. Now I don't know what the natural log of 2 is, but do I know what the tangent inverse of 1 is? Yeah. Tangent inverse of 1, if that's, say, y, then tangent of y must be 1, and y is between negative pi halves and pi halves. And so when is the tangent function equal to 1? At pi over 4. Tangent of pi over 4 is 1, and that's between negative pi halves and pi halves. And so our final answer is pi over 4 minus 1/2 the natural log of 2. And I don't know what the natural log of 2 is. I mean, I can approximate it, but there's the exact answer. Okay. Well, let's take a look at one more example then. So you can see we can use the integration by parts formula to find the natural log antiderivative, which we did, and now the inverse tangent natural antiderivative. You can also do the inverse sine function, for example, doing it this way. Let's take a look at this example. Go back to maybe a little bit what we were dealing with before. Again, the antiderivative of this is just not find the antiderivative of x squared, which is what, x cubed divided by 3. Find the antiderivative of sine of x, which is what, negative cosine x, and then multiply the two together. That if you do that, that totally means you haven't watched any of this video or you haven't done anything in terms of integration by parts. So no, we're going to use integration by parts. We're going to choose our u by Liate L. Liate L is log, no log function. I is inverse trig, no inverse trig. A is algebraic. Yes, there's algebraic, and that is x squared. The dv is everything else. Okay. So my du, the derivative, is 2x dx. Antiderivative of sine x is negative cosine of x. So you've got to remember these rules, right? When you integrate sine, you get negative cosine x. If you take the derivative of sine, you get positive cosine of x. So this means that this integral is equal to uv, so that's a negative x squared cosine of x, minus the integral v, which is negative cosine x, v du, which is 2x dx. Let's clean this up a little bit. Negative times negative is positive, notice. And I've got a 2x cosine x dx. Well, has our integral gotten simpler? X squared sine of x is now 2x cosine of x. Sine x and cosine x are about equally challenging, but x squared to 2x, yeah, 2x is simpler. But we're still not there. I can't just integrate x and integrate cosine x and multiply. I'm not at a form that I can evaluate yet. So what do I need to do? I need to do integration by parts again. Remember, I abbreviate integration by parts as IBP. This time I'm going to choose u to be the algebraic 2x and dv to be cosine x dx. So again, hopefully, I'm going to see a trend. It got simpler. Let's see if it gets simpler to something I can evaluate. Du is just 2 dx, and the integral of cosine of x is sine of x. And so this becomes, don't forget I got this negative x squared cosine of x plus, and then here I'm going to do what? Again, uv, so that's 2x sine of x minus integral v sine of x du, which is 2 dx. All right. Well, this I can do, right? Because this 2 can come out, right? This is just the integral of what? 2 times sine of x dx. And that's simpler, right? There's no x with it anymore, right? It was x squared sine of x, and now it's just sine of x. Yeah, I can do that one. The antiderivative of sine of x is what? Is negative cosine of x. And so cleaning this up, I get negative x squared cosine of x plus 2x sine of x minus times minus plus, minus times minus plus 2, all right, don't forget your 2, cosine of x. Okay, so you can see sometimes we have to do integration by parts again. What do you think would happen if I started with x cubed sine of x? Then this would involve, something x, 3x squared cosine of x. And then here I would still have an x with this, and I'd have to do what? Integration by parts again. So 3 times. So you can see you might have to do integration by parts 2 or 3 times. Okay. If it was x to the 7th times sine of x, we have to do integration by parts 7 times. Now there is a sort of tabular method. There's a pattern to this, and that tabular method can help you get the integration by parts result a little bit quicker, but it kind of hides the process, and so I'm not going to give you x to the 7th sine of x as a problem to do. But if you check the tabular method, that's a kind of a neat way to organize and get results for something like that. Okay, but the bottom line is you might have to do integration by parts 2 or maybe 3 times. Okay, well, we're going to stop there. The next example we will look at in the next video is I might have you might have your head spinning. We'll just say, little pun there. We'll look at that in the next video.